Good morning, everyone. Welcome to lecture 21 today. We are almost at I believe it's half of the semester, no? Total 42 lectures. So, in the last class, we derived the equation of linear momentum balance, right? And just to give you a recap, the equation was in the tensor form the following. Okay. And this is also Eulerian form, right? Because all the measures here are Eulerian. See, even sigma, the stress tensor, it's also called Eulerian stress tensor. Why it's called Eulerian stress tensor? Because what it takes as an argument, this normal, that's the deformed normal, the normal in the deformed configuration. Okay, so whatever is the current normal, that normal has to be supplied here. So again, I have this body, it has gotten deformed, and maybe you cut a section here, and this section may have been like this over here. Okay, but it's the current normal that matters for sigma. So you pass the current normal n here, and it then gives you whatever is the traction acting on this internal section T. Okay, so that is why it's also called this Cauchy stress tensor sigma is also called Eulerian stress tensor. So sigma has another name which is Eulerian stress tensor. Okay, so somebody is asking linear momentum balance derivation which we derived in terms of momentum flux. If we apply for solids, is it valid for a small organism or any? It's for any order of deformation. See the equation that we have derived, nowhere we said that let us restrict the deformation to be small. It holds for any order of deformation, okay? The recording has already started. Okay, so this is the linear momentum balance in Eulerian form. We'll now like to derive the same in a sort of in Lagrangian form. All right. So let's see what I mean by that also. So again, the physical principle is the same that net force is equal to rate of change of linear momentum for any part P of the body. So any part P is again occupying dt in the current configuration and d ref in the reference configuration, right? So supposing here is your d ref, which is getting deformed to dt, and then you know that on it we have those traction forces, right? And these traction forces need not be perpendicular to the surface, and this allows you to have shear component of traction also, and of course normal component is there too. So that is the traction T, and that's a function of current location y, and obviously the time t, and also the normal n. Okay, so and then you have the body forces also. This is something that we have seen, which we denote by b, and then you summed it and equated it to rate of change of linear momentum of this part dt. Let us write that again. So we have integration over the surface, which is del dt of, okay, I should write t only first of all to begin with. So t and then day plus triple integration over the volume dt b dvy, and that's equal to d dt, which is a material time derivative of the total linear momentum, which is rho times velocity dvy, right? So you remember in the last class we converted everything to dt, to the Eulerian domain, to the current domain. Can we think of converting all of these terms to the reference domain, that is dref? So that is what we want to see here. Okay, so let us try to do that, converting them all to the reference configuration. I mean, the domain of the integration. So you remember that these are Eulerian, so I'll just make it b bar to be more explicit. They are rho bar and this is v bar. Okay, so let us take this term for example. So if you want to make a change of variable formula, then you could write it as dref, and then here you have this b bar function, but then induced through the deformation map y hat of x comma t into j, which is of x comma t times dvx, right? And this is how you have converted this um, integration to reference domain, right? And likewise on the right hand side, this you can write as d dt integration over dt, the current region of the part of the body, and then again you sorry, I want to make it dref, so this becomes dref, and you have this rho bar as a function of y hat of x comma t, and likewise you can think of this v bar also, and then you have this j and dvx, right? And then you use mass continuity to say that this rho bar times g is rho naught, right? Referential mass density. So this is then d dt of d ref rho naught, and rho naught, you know that it's just a function of x, it's independent of time, times v bar dvx. Okay, and then you bring this dy dt inside, and you had seen this finally becomes, and you see that this v bar, now that you have changed to dref, you could also write it as v hat, no? So this can always return as v hat, and likewise even on the top, this v bar is actually now v hat, because v bar is same as v hat, so you can just do that. And then when you bring this dy dt inside, it's only going to act on this v hat, and you have to take the material time derivative, and then this is going to simply give you acceleration, right? Rho naught of x into acceleration. So what you see is the two of the terms very easily got converted into dref, into an integration over dref. Two of them are easily done. Of course, the last one is not so easy. And you will see that to do it, we have to introduce some new, and we'll get introduced to a new measure, or a new quantity. So of course, it's a integration over the current surface. Then if you want to make it Lagrangian, you have to change it to the referential surface, isn't it? So we can do that, and it becomes del d ref, and t, let us write this as sigma into n dA y. So okay, so in between we have this step, del dt sigma n dA y. Okay, and this n dA y, how do you write this in terms of the referential surface? So we have already seen the transformation of area, right? And I think that is J times F inverse transpose and DAX. No, there is also this M. Sorry, this is NX, right? So this is, if this is the current normal NY, then this is NX DAX. I hope that I am right. Someone can please confirm to me that what I wrote is correct. And then this sigma is obviously written as, so you can also write as sigma hat. So it is such that sigma hat of x is simply sigma bar, the Eulerian, and y hat of x comma t comma t. Okay, so sigma hat of course is also a function of time. Okay, so this is what it is. So let me write a bit more nicely. So this becomes del d ref, and then you have here j times sigma hat F inverse transpose. So you have this quantity multiplied with nx times dAx. Okay. And let us compare these two integrals. Can someone tell me what you see? Is there some kind of similarity in the two integrals? See, what we are doing is simple change of variable from current surface to referential surface. Okay. So don't you see that here also you have day, here you have dax, here you have ny, here you have nx, and then here you have some second order tensor, and here you have a second order tensor but something else. And this second order tensor takes nx. Okay, so this is taking nx as an input, which is the undeformed normal. Okay, so this has got a name, and this is also called first Piola-Kirchhoff stress tensor. Okay, so most of you would have heard this for the first time. This is also called first Piola-Kirchhoff stress tensor. Okay, and let's denote this by P. Okay, and it's a function of x comma time t. So the relationship between P and sigma, you can see it here, that P is equal to J times sigma F inverse transpose, or sigma is equal to 1 over J P F transpose. Okay, so this is, I'll tell you again, this is first Piola-Kirchhoff stress tensor, a new stress tensor. But it is basically for mathematical convenience, because we wanted to convert our integral to referential surface. And that's how we came across this. Okay, this is not something that is acting on the surface or acting in the body. Even the stress tensor sigma is also not something that is acting in the body. What is acting in the body is the traction T. So when you cut a section, then you would see that traction T appearing. And that traction T depends on what section you are cutting. If you take a section of different normal, you get a different traction. That is why that traction is also dependent on the section normal N. And so mathematically, that traction induces this sigma, stress tensor sigma. Okay, so sigma is also kind of abstract quantity, but it's a nice thing, so that you get traction on any plane just by sigma times n. And this likewise, this first Euler-Kirchhoff is also an abstract quantity. So what is it? But of course you can think of some physics behind it. Let's try to see that. So if I again look at these two integrals and just have a look at the integrand, then isn't it that we are saying that sigma ny day is equal to p nx dax? Isn't it? That is what we are saying. And if you try to draw some picture, so I'll again have the referential body and the deformed body. And in the deformed body, you have this small surface patch, okay, which is having normal nx, and the area is dax. Okay, so that's a surface vector nx dax. Okay, and this has an analog in the reference configuration, right? So it will be something like this, but here it is, sorry, here it is ny dy, right? In the deformed it is ny dy, whereas over here it is nx dax. So what is then P giving us? What is the meaning of P then? The P simply acts on the referential surface vector to give you the traction that is acting in the corresponding deformed surface vector. Okay, so let me write that here. P simply acts on the referential surface vector which is nx dax together, to give traction P times day. So it is not just traction, it is traction T times day. The total force due to traction. Or I should say give traction force on the corresponding deformed surface vector. Okay, I hope this is clear to all of you. And if somebody asks me, what is P times Nx giving? What is this equal to? So let us just try to work out and see what is this giving you. So we have all seen that P times Nx day, that's equal to sigma times Ny day. Okay, on the left hand side is dax. Okay, so but sigma times Ny is same as traction times day, which is the total traction force. So P times Nx, if you denote this by T naught, okay, if you denote this as T naught, then so this thing, if it is T naught, then T naught is equal to T into day over dax. So can someone tell me how are T naught and T related? Can you think of some physical meaning for T naught after looking at this mathematical formula? Physically, how they are related now? Yeah, T naught and T are obviously in the same direction, isn't it? T naught and T are in the same direction. So T, what was T? This is traction, right? And this is actually, you can say that it's kind of traction force per unit current area, right? So when you cut a section, you have that traction force divided by the current area, you get this traction T, right? Whereas this T naught is then the same traction force. That means when you cut a section in the current configuration, then on the section you have some force due to traction. And that force, if you divide by undeformed area, corresponding undeformed area, the corresponding undeformed area, that gives you T naught. Okay, so that's the meaning of T naught, like Swam has also written, traction force per unit referential area. Okay, so P times Nx is giving you that T naught. Don't think that again that T naught is acting in the reference configuration. That is not true. Just like V hat was not the velocity in the reference configuration. V hat was equal to V bar, right? So likewise, T naught is not something that is acting in the reference configuration. What is acting is T in the current configuration. And T naught is simply proportional to that T. And the physical meaning is it's the same traction force but per unit referential area. Is it clear to everyone? So nothing is really acting in the reference configuration. Only the best function that we have as of now is that rho naught. So rho naught is indeed the mass density in the reference configuration. You can only say this for the reference configuration, mass density in the reference configuration. So this rho naught is something which really belongs to reference configuration. Rest all, none of them belong to reference configuration. V hat, A hat, or this T naught, none of them belong to reference configuration. They are just written in terms of referential coordinates. So T naught is just a function of x and the undeformed normal. So T naught is therefore the function of x and the undeformed normal nx. And P likewise is just a function of x. So you can see that because they are functions of undeformed quantities, so they are Lagrangian functions, right? And therefore this P is also often called Lagrangian stress tensor. There are of course several other forms of stress tensor. So what we saw is the first Piola-Kirchhoff stress tensor. Then there is also something called second Piola-Kirchhoff stress tensor. Then there is something called Biot stress tensor. But let's not get trapped in so many stress tensor for now. Okay, but I'll just write it here. But let's not bother about them for now. Okay. But yeah, first Piola-Kirchhoff indeed. This is something that we got introduced to. A very nice quantity which allows us to write down or convert this deformed surface integration to undeformed surface integration, isn't it? And now we can rewrite the LMB integral form in the Lagrangian formulation. So what we have now is integration over d ref p times nx dax plus you have this b, and I'll say b hat because it is induced through that deformation map, no? P hat of x comma t and times j. And remember that this b hat, so b hat is same as b bar, right? Which is a function of y comma t. So into dvx, and that is equal to, so this is del d ref, this is d ref, this is again d ref rho naught a hat. Okay, now what do you think what should be done? Yes, of course, T naught is also a function of time. Did I miss that? Yeah, so yeah, T naught is indeed a function of time too, because you see the way it is worked out. So T naught is also a function of time and this normal nx. And likewise, this P is also a function of x and time. Suppose the surface integration has to be converted to volume integration. Yeah, so, and you do remember how we did it for sigma ny day, right? The same way this is also going to happen, and I'll just write down the final result. That this converts to d ref divergence, but this is now the Lagrangian divergence dot with p dvx. Okay, so you see it's now Lagrangian divergence. And finally, when you bring them all together, then you have the integration over d ref, and you have this Lagrangian divergence plus j times b hat minus rho naught a hat, and that's equal to 0. Okay, and now we will say that because it holds for any d ref, because it holds for any part of the body, so d ref is arbitrary, right? It can be as small as possible, which allows us to use the localization argument. So now we can use the localization argument and then say that the integrand must vanish. And this gives us the equation for linear momentum balance in the Lagrangian formulation. Sorry, this is I can say here it's equal to this. So that's the Lagrangian form of LMB. Okay, is that okay with everyone? Yeah, so dvx is missing here. So very interesting, no? Even the Lagrangian form is quite nice. And the P did the trick. This P is very much acting like the sigma. And instead of Eulerian divergence, you have here Lagrangian divergence. So these are the major changes. And also you see that instead of current density, you have the known referential density. So rho naught is not an unknown, rho naught is known. It's a known quantity because when you choose the referential configuration, then you also get to know what is rho naught. Okay. Okay, so that is just the linear momentum balance. And this is going to hold for any body, whether it is solid or fluid, both Lagrangian and Eulerian form, they hold for any body, any continuum body undergoing any kind of deformation, whether it is purely elastic or it is viscoelastic or it is elastoplastic, viscoelastoplastic, whatever kind of deformation you can think of, or fracture is happening, whatever, this equation does not change. Because you see, while deriving this equation, we never said or we never restricted anything by saying that okay, this is holding only for plastic deformation or this is just for viscoelastic deformation. So it's a general deformation. Okay, so this equation remains the same irrespective of what kind of deformation you are dealing with or what kind of body you have. Only restriction is that we are dealing with a continuum framework. That is all. So I hope this is clear to every one of you. Okay, so having derived this linear momentum balance, then of course there is another one which is called angular momentum balance. So Subham says in fracture F will become non-invertible. That is not true. Why would F become non-invertible? You have a void appearing or gap appears, the displacement becomes discontinuous, but F does not become non-invertible. Okay, Chaitanya is asking, explain its interpretation in terms of control volume, like we did for Eulerian one. See here, this is in terms of reference body, right? It's the reference body dref, which is not changing with time. So, I mean, it's not just it is not changing with time, also it contains the same set of particles, dref. So it's always the same set of particles. So you don't have the analogous control volume here. Because in fluid mechanics, the control volume that you had different set of particles in it at different time. But this dref always has the same set of particles. Of course, the dt also had the same set of particles, but you could think that if you think of the um, same volume in the space as occupied by current dt, then that is sort of control volume. But here you don't have anything like that. dref is the volume occupied by the body in the reference configuration. Okay, so Chetan is asking, it's better to analyze in Lagrangian terms. It's a very nice question. So because you are thinking that, oh, the domain is not changing, the domain is fixed, so you are always doing solving a problem over a fixed domain. So it's really nice in that way. Also, there are several nice things about this Lagrangian form. Now that you brought this question, we can discuss it. So you have divergence of P plus J times B is equal to rho naught, and this acceleration A hat is simply del 2 y over del T2. Okay, it has only this. Or you could also say it is rho naught del V by del T, and of course it's del V hat. Whereas the Eulerian equation, let me try to write that. I wanted to come to that later on, but it's okay. And you see the acceleration is so messy here. It is del V bar by del T plus the Eulerian gradient of velocity times velocity, right? So you see that this convective acceleration, this is non-linear in V. And also this rho bar here is unknown. Plus the domain dt is changing. But of course, you could think of this for a control volume. In that case, control volume could be fixed. Okay. But otherwise, if you think of dt, then it is changing. Whereas over here, you see that rho naught, this is known. This is simple. And d ref is fixed. So don't you think Lagrangian form is really nice? What do you say? Isn't it? Anyone disagreeing with me? What about people in fluid mechanics? They will be really angry. How can sir say that Lagrangian form is nice? So Nikhil, by the way, in the meantime, asked a question that the two integrands were performed over same set of particles. Yes, indeed. That is why you could write ny day as j times f inverse transpose nx dax, right? Because then only they relate the same areas, corresponding areas. So Shubham is saying it's not nice because you have to track every particle. So forget about that we're tracking. Otherwise, from maths perspective, what do you think? Is it nice? Suppose the equations are given to you and you don't have to really go in the experiment and track the particle. Suppose you are just doing computer solving, then is the Lagrangian form nice always? So Chaitanya is saying yes. Anybody's disagreeing? People from fluid mechanics? Of course, this nonlinear term is a really messy term. This induces, I mean, this brings all the hell. And this is also, what is called Navier-Stokes equation in fluid mechanics. You just have to replace sigma with the corresponding constitutive form for sigma. But otherwise, the convective term is really messy. See, what we are trying to solve here is in fluid mechanics, we are often happy just getting the velocity field. And in solid mechanics, we want to get the y, the deformation y. But even then, it's not like the Lagrangian form is always good. It's because you see, you still have these unknowns, p and sigma. You have to relate these p and sigma to the kinematics, which is position y and the velocity v. And that relationship between p and so relating, so I'll write that relating p comma sigma to kinematic variable, which is y and v, is still to be done, right? And it turns out for fluid mechanics, relating sigma to kinematic variable is much easier. It has a much nicer form, whereas relating p to kinematic variable is messy for fluid-like bodies. Whereas for solid-like body, it's the other way. Relating p to kinematic variable is easier. So that is what flips this Eulerian form of equation in the favor of fluid mechanics. Okay. Otherwise, of course, you have this messy term to deal with, and if you say that you have a steady flow and you neglect this higher order term, then you can do lots of interesting things in fluid mechanics. I won't be able to introduce the angular momentum balance. So we did till now linear momentum balance, and the next thing to do is angular momentum balance. Okay, so let's do it in the next class because I will only be able to barely introduce it. So in the meantime, if you have any question, please feel free to ask me. I'm going to unmute all of you.
Sir, I was saying that while the fracture is going on,
Yes.
if we consider a small line element, it is splitting into two line elements, right?
Yeah.
So in that case, F will not be one-to-one relationship, I think.
Okay, so I think the neighborhood of the point is changing there. If you restrict the neighborhood, see, suppose a point lies on the surface of fracture. Then before fracture, that point had all its surrounding volume as part of its neighbor. But after fracture, one half of the neighborhood is on one side of the fracture and other half is on the other side of the fracture. So if you restrict the neighborhood, then you will have two different F's applied to two different neighborhoods. And then things will work out. You don't need to have non-invertible F.
Okay, sir, got it.
Yes, good morning. Sir, actually, the above where we have related P with our sigma, so their domains were different, no, dt and dref, but integrand we equated it. I could not follow.
Okay, that's a good question.
One is dt, another is dref. So, but integrand, I think as it is, we have equated.
So I guess you are saying here, no?
Yes, the last this J sigma hat F inverse transpose nx dx. Yeah. This expression,
Right.
how did we write? Yeah.
See, it's basically, can't you think that this is indeed for the same set of particles? If you think of it as integration over, kind of material particles, then it is indeed over same set of particles. No?
Yes, sir. But when we think dt is changing, okay, for corresponding those changing set only, we are having dref also.
Yes, yes.
Different set of dt if we choose, then in reference also different set of dref may come.
Exactly, yes.
Okay.
It's
Then,
just that if you make the same domain, if you make both of them same domain, then you won't be able to derive this result. That is why I didn't do that. Because you
got
see,
it.
one of them has DAY and the other has DAX. So it indeed has to be different domains.
Yeah, I understood, sir.
But what you see is that NYDAY corresponds to the same set of particles that NXDAX has. And then when you think of particle-wise integration being done, then in the domain of particles, it's the same set of particles, and therefore you can relate them, right?
Yeah, understood.
Okay.
And this tractions are actually like, I mean, in deformed also, we are just taking the area part. I mean, it is actually the quantity in the we are taking into consideration when we say about T naught and T.
Yeah.
So this is the traction force which is there in the deformed body only. But
Yes, it's
one
in the
time
deformed
we are
body.
taking with respect to the current area there, another time corresponding deformed area from there.
Yes, very good. That is what it is. So traction force is always the force in the current area because that is what is experiencing force. The reference
Okay.
configuration is just a fictitious configuration. It's an imaginary thing.
Okay.
Of
Okay.
course, of course, sometimes we choose it to be the configuration at t equal to 0, but otherwise it's like an imaginary thing. So nothing is really happening in the reference configuration.
But sometimes to change the variable and all, like body force or traction, we are just changing the variable and then equating it for referential and our deformed also.
Yes.
But there we are also like assuming that then it is acting in the undeformed configuration also, no? Like
No. When? For which one, for example?
like say b body force b bar we are relating with our like deformation map and going to b hat also
Yes.
in so
So B
when we
hat.
are doing
So again, B hat is not something that is acting in the reference configuration. B hat is again
okay, okay,
acting in
got
the
it.
deformed configuration.
Okay, understood, sir. Yeah, when we go for relating it, it may get related with respect to this only area or volume of the undeformed we will take. The
Yes.
quantity will be in the current only in this
Yes.
case.
Quantity is always acting in the current configuration.
Okay, sir,
The
understood,
only
sir.
exception is this rho naught. It is indeed belonging to reference configuration.
Okay, because it's a static function, so I think it can belong
Yes.
to.
Correct. Correct.
Okay, sir. Okay, okay. Thank you.
It's the same, like a similar, like rho in the Lagrangian configuration. How did you equate it to rho naught, which is a fixed, constant quantity?
No, I'm not equating rho to rho naught. Rho,
Then,
which
like
is
in the first
the
page.
in the first page. Where?
So then,
Here. Yeah, so what I'm saying is rho naught is equal to rho bar times J. Right? You see? This rho bar and J together is forming this rho naught.
Okay, got it, sir.
Sir, I'm still not clear about the thing discussed right now. Equating two different integrals with different domains, d
No,
reference and dt.
we are not integrating the two.
Equating, sir, equating.
Okay,
We were
I think
equating.
let me explain that to you in a bit more through pictures. So suppose again this is the reference body and that's the undeformed body, and here you have some area, some finite area, okay, and then here also you have the corresponding deformed area. So they are the corresponding areas, by the way. All right. And then a small area here will be some small area over here. And this has the surface vector NYDAY. Okay. Whereas over here, the surface vector is NXDAX. Okay. So of course, nx dax is not equal to ny day, right? Nx dax is not equal to ny day. That is 100% known. But what we are saying now is that the p, the quantity p, we want to bring it in such a way that p times nx dax is equal to sigma times ny dy. So this p is defined that way. So P is such that this should hold. And if that is the case, can we relate P and sigma? So you see, now I'm going in an opposite way. Suppose I want to have a P such that P times nx dax is equal to sigma times ny dy. Okay? Are you with me, Chaitanya?
Yes, sir. Yes, sir.
Okay. Then what should be done? Then in that case, on the right hand side, can I write ny dy as J times F inverse transpose into NX DAX? Can I do that?
Yes, sir.
And then, since they have to be equal, this means P minus sigma J F inverse transpose times NX DAX is equal to 0, right? Okay. And then because it has, we want this to be for all normals. So therefore the thing inside the bracket would be 0. And that means our P, you can, if you choose your P to be like this, then you can do what you wanted to do in the beginning. So this is a reverse way to do the same thing. Is that okay? Do you like this part?
Yes, sir. But I was asking that as their domains were different, so when we equated them at the first step, how could we equate them? Because one domain was dt and other was d reference. There I was facing problems, sir.
See, in this way of derivation, this is not correct. This is what you're saying. Domains are not same, and of course they are physically also they are not correct. One is referential surface and other is deformed surface.
Yes, sir.
But then I'm saying let us introduce a P. Let us think of a P so that it will be equal.
Okay, sir. That I understood. Yes.
Yes, so I'm saying that can we have a P so that these two are equal?
Okay, okay.